Hi, my name is Tanner and I represent my colleagues Daniil, Jan, and Samuel. We were supervised by Nick, Debbie, Jan, and Peter. We co-wrote a paper on a simulation showing defense against an APT attack. This method is based on a behavioral model that we created and will be further explained in this presentation. Besides aiding in the defense against an APT attack, we also focused on how such an attack can be detected on an organizational level. As for the definition of an APT attack, it is a sophisticated and generally well-resourced cyber attack with the goal of mining sensitive data while remaining undetected. Some additional characteristics of such an attack that are of particular importance to our model and are specified by the National Institute of Standards and Technology is that they take place over an extended period of time, that the attacker continuously adapts to the efforts of the defenders, and that the attacker consistently interacts with the target network in order to reach their objectives. Our model is based on two key pieces of research, the cyber kill chain and the MITRE, ATT, and CK attacks and techniques. The kill chain visualizes the 7 steps that a cyber adversary must complete to achieve their goal. The MITRE, ATT, and CK portrays common attack methods and possible exploits. A paper we found combines these two into a single model and allows defenders to predict and respond to an attack. Here at the top of the screen, you see those 7 steps, and below it, you have the corresponding methods and exploits. On the side, there are several APT attacks and the specific attack paths they have followed. Our model is based on the stages and methods of APT attacks described in this table. I will now pass you on to my colleague.
Hello, my name is Samuel, and I will walk you through our network model. It's basically divided into 4 parts, the first one being the cyber kill chain. This part represents how the attack unfolds in time. The next one is the organizational understanding, which represents the organization trying to figure out what is going on in the actual attack. This part of the model informs the next part, which is the organizational response, where the organization responds to the attack and tries to suppress it based on their correct understanding of the attack. And lastly, we have the organizational controls, which are just meant to prevent the organization from overreacting. In the next slides, we will look into each of these parts in detail. Here you can see the close-up of the cyber kill chain part of the model. It gets its input from the contextual states on the left to the base layer, and the base layer represents individual steps of the cyber kill chain from left to right, from reconnaissance all the way to action objectives. When you see the states doubled or tripled on one of the steps, that represents multiple attack methods as they were identified in the table shown to you by my colleague. Then we have the first order adaptive layer of the model, which simulates adaptive thresholds and weights. The thresholds represent vulnerabilities in the system. So if a threshold for one of the states is lower, it makes it more excitable and less input is required to increase it and progress to that part of the kill chain. Then we have the adaptive weights, which represents attackers making progress through the kill chain. So if they actually manage to excite one of the states on the base layer, most likely because the threshold was lower, they solidify the connection to that state, symbolizing them making progress. Here you can see the close-up of the organizational understanding part of the model, which represents organization trying to detect and predict what is going to happen in the cyber kill chain part of the model shown previously. We have a very similar layout of the whole model with the first order adaptive layer thresholds represented and all the steps of the cyber kill chain represented. And this part of the model basically gets inputs in 2 ways. The first is through a connection between the base layers of this part and the cyber kill chain part, which represents correlational alert from the system that provide an indication for an organization what is going on. However, is not exactly enough for them to determine what type of attack is happening. Then secondly, we have connections between first order adaptive layer thresholds, which is organization trying to understand over time where its vulnerabilities lie. Of course, some of this understanding is faulty, which will result in organization not understanding correctly what is going on. And how is the understanding represented? Organization understands what is going on if this part of the model, or if the input flows in the same way through this part of the model as through the previous part. You can see the organizational response part of the model, representing the organization trying to suppress the attack. What happens here is that there is a contextual state providing constant input to the base layer, which is connected to the first order adaptive thresholds in the cyber kill chain part of the model. So what happens if an input actually manages to fall through? It increases the thresholds, basically making the steps of the cyber kill chain less excitable and blocking the attackers from progressing. However, the flow of inputs is blocked by the first order adaptive layer of weight, which is initially very low, but it can get increased by organization predicting in the organizational understanding part of the model that there is something going on. This would increase the weight and try to suppress the attack where they think it is. If they predict incorrectly where it is, they're going to try to suppress the wrong part of the cyber kill chain, resulting in it being not effective. And lastly, we have first order adaptive layer of speed, which means to prevent the organization from reacting too soon and wants to make the response a bit slower. Here you can see an outcome of our simulation. However, because this is not readable at all, we're going to look at it piece by piece. Here you can see the behavior of the states in the cyber kill chain part of the model, so the attack itself happening. When the value of these states increases up, that of course represents cyber attackers making progress. In this particular model, we can see them increase and then afterwards decrease, which means they were successful at first, but then they were suppressed. You can see that differences in organizational understanding of their vulnerabilities in the system, resulted in attackers making different amount of progress in different stages of the cyber kill chain, and that was because our organization knew better what is going on and they could suppress one of the attack paths better than the other. Okay, also in this model, we have only limited actionable objectives because the organization responded to the attack fast and suppressed it. So here you can see the organizational response part of the model and how it behaved. So in our simulation, it did suppress the attack. You can see the high parts of the diagram, and that's where the suppression happened. At the beginning, they all start on 0.5, which represents basic maintenance of the system by the organization. And this is necessary to prevent the attackers from fully progressing through the model, to give them some resistance. However, this alone is not enough to suppress the attack. It needs to increase higher based on the correct organizational understanding. The speed factor of how fast, so basically how fast the states can change, increased over time, and this is the role of organizational controls that were meant to prevent it from overreacting. This diagram shows a selection of states from all parts of the model to show how the whole loop works. So let's start here. Here we can see the states representing the threshold in cyber kill chain and in organizational understanding are very similar, which represents them organization correctly understanding their vulnerabilities. Afterwards, we can see attackers making progress in the weaponization host-based stage, which in turn decreases further the threshold, basically exploiting the vulnerability in the system. You can see that the organization is adapting to this there slowly, and because they sense this decrease in the threshold, however slower than it actually happened, it increases the response and triggers the response, which we can see right here, which in turn suppresses the attack afterwards. The kind of a loop described in the previous diagram happens for every stage of the cyber kill chain, and they all tie together and influence each other. And here we can see a small cutout of how weaponization host-based is going to affect delivery the delivery stage of the cyber kill chain. We can see that first, the delivery stage is triggered by weaponization because the organization did not manage to suppress it in time. However, afterwards, as they suppress it, they also suppress both weaponization and delivery. As a proof of concept for the model, we did a probabilistic what-if analysis where we picked four if factors, where we monitored the outcomes of them, and for each if factor occurring, we picked a probability on some basic assumptions. Of course, these probabilities are not very accurate because they are picked on only based on the assumptions we described in the table. For more accurate probabilities, we would need different type of data, but this is enough for a proof of concept. So the first if factor is the vulnerability of the weaponization stage being faster or slower to influence. So what we are changing is the speed factor of the adaptive thresholds in the cyber kill chain part of the model. The second if factor is the progress of the delivery stage being faster or slower to increase. So here we are changing the speed factor of the adaptive weights, again in the cyber kill chain part of the model. The next one is the correction speed of the incorrect organizational understanding of its vulnerability being slower or faster. And what this represents is how fast an organization can correct an incorrect assumption they have had. So how fast can they correct their mistake? The last if category is very similar, and it's the correction speed of the correct organizational understanding of the vulnerability being slower or faster. So how fast can an organization upkeep its knowledge, which is currently correct, in case there are any other new developments or occurrences? These were the four if categories, and now I will pass you on to my colleague who will explain the what categories.
We were monitoring three what categories, the first of which being attackers achieved actions on objectives, the second of which being attackers achieved command and control, but not action on objectives, and the last of which is that the attackers did not achieve actions on objectives or command and control. In this example, you can see attackers fully progressing through the kill chain and achieving both command and control and action on objectives, both of them highlighted in purple and green respectively. In this example, the second scenario, you can see attackers achieving limited action on objectives, and even though they are barely visible, these are shown by the small double squares in the middle bottom of your screen. And in this final objective, you can see the attackers achieving neither action on objectives nor command and control, and becoming suppressed in the early stages of the attack. This provides us an example of risk based on the values we input for the model, giving us medium risk for attackers achieved AOO, low risk for attackers achieved CNC not AOO, and low risk for attackers did not achieve AOO or CNC. When we further investigated the iterations of the simulation, we found that what predominantly determined the attacker's ability to achieve action on objectives was a low organizational monitoring accuracy of the correctly assumed vulnerabilities. These are part of the system that were not vulnerable in reality, but the lower upkeep levels from the organization allowed creation of vulnerabilities in them. This also tells us about the nature of modeling vulnerabilities in a network model. It cannot be represented as just one abstract state. Vulnerabilities are influenced by detection speed, adjustment capacity, and response capacity. Lastly, we have a limited optimization issues with the model, as we selected all the values in the network manually. This could be solved in the future by using various optimization tools, such as MathWorks Optimization Toolbox. Thanks for listening.